Hey everyone, welcome into this lecture number 22 of the semester. This lecture is going to cover surface area, and while we cannot, maybe we could try to figure out how to compute the surface area of just a generic surface, we are going to set this up in a way that might look familiar. We're going to try to compute the surface area of a surface of revolution. So let's suppose that we have a curve, and I'm going to draw this curve as a function of x, probably, just for the sake of the setup. But we'll see in the future it can be a little bit different. But let's say we have a curve segment between 2 points, A and B. Obviously these will have y values, C and D, and then I'll connect the curve in orange, I guess. I'm going to draw this so that it's not too crazy right now, because the next thing we're going to do is, so again, we're assuming for the sake of this argument that this is the curve given by a function, y equals f of x. And now what we're going to do is we're going to create a surface, okay, by rotating this curve out of the screen and around. So around the x-axis, for example. You could rotate this around the y-axis, around any line, actually, and we'll have a similar situation. But again, for the sake of the setup, let's rotate this around the x-axis and see how that works. So everything's going to rotate around the x-axis. That starts with the endpoints, right? So the two endpoints are going to rotate around, and then everything in between. So I'm going to try to make this look as though it were symmetric. For me, that's not bad. All right, you can probably do better. But then the idea is that everything is rotated, including a little segment here. So in particular, like this little segment. So this little segment that sits above. So we're going to try to compute the surface area, right? And so I'm kind of looking ahead here, but this little segment has been swept around and looks something like this, right? All right, so the basic idea here, as usual, is going to be, and when I say as usual, you know, we're in a chapter that's studying integrals, and we've spent a lot of time learning how to compute integrals. And so now we're trying to use these integrals to do something, right? And so the idea here is that we are going to chop up, just as I indicated here with this strip that I've drawn, right? The idea here is that we are going to chop up our, I'll do it in blue, our interval from A to B. We're going to chop it up into a partition. And so I'm going to make sure those 2 points that I already used are part of our partition. And remember, the rules of our partition are that you have to start with x0 as the first point, and your last point has to be xn, and then they have to increase, right? They have to increase. So we've got this x0 equals a, less than x1, less than x2, etc., all the way out to xn, which is our endpoint b. So there's our partition. And then above each partition, we'll chop up the curve, right? And as we rotate that curve section around, we get a little cylinder, right? And so the one that I'm looking at here is this partition. And so that is going to be what? Probably a delta x, I will call it, right? That's the width right there. The height of this is going to be something to do with the function. So we can choose a test point to find the height of this curve. And then we're going to chop this thing up, right? So, I mean, let's just say somewhere in here, this height right here is f of xi with a star. All right, and we're going to chop this up, and we're going to then pull this out. So if we pull out this cylinder and we try to look at it, then what's it going to look like? Oh, I'm going to pull it out and then also kind of redraw it so that we can get a better look here. So here's our cylinder, and we're going to try to find the surface area of the surface, right? So what does that mean that we need to do in terms of the cylinder? Well, that means we need to compute the area of the cylinder, right? And again, in our mind, if we were to kind of cut this cylinder right here and roll it out, well, what's a cylinder become when it's been cut and kind of rolled out? It becomes a rectangle, right? And so the area, the surface area of this cylinder is just going to be equal to the area of this elongated rectangle, right? Where the rectangle's base is equal to the circumference here, right? That all becomes, say, the base. And then the height of the rectangle down here is the same as the height of the cylinder, but that height of that whole thing right here is like the length of the curve right there, right? And so it turns out, and again, your book does this pretty well, so I'm just kind of doing the setup here just so that we can use it to do examples. But it turns out that we have to measure, number one, the circumference here has to be, right, what is it? It's 2 pi r, right? 2 pi r, but what's r? R is the height of the curve, right? So this, which would normally be 2 pi times the radius. The radius of the cylinder is the height of the curve that we started with. All right, so this is then 2 pi times f of xi star. And then what's this going to be? Well, that's going to be the length of the curve on that segment. So the length of the curve we're going to call ds, right, or delta s in this case, delta si, as a function of x though. So we've chopped this all up in terms of x. So that's the arc length. We're going to approximate the length of this curve by its delta s. And so that part right there, so that's obviously the height of the cylinder, right? And down here we're going to say, all right, well that's delta s of x sub I or something. It gets weird notating it like this, right? And so now we know what to do though, right? Because now the area, so what we might call delta A sub I, this is just equal to the area of this rectangle, right? The surface area of the surface is then going to be 2 pi times f of xi with a star times delta s xi, right? So times this is the surface area element down here. Okay, and what else do we have to do? Well, by the way, you know, there are different ways to write this down. Just the way that I've set it up with this curve being a function of x, this is exactly what we get. And so then, of course, what the total surface area is going to be the limit as n approaches infinity of the sum, I goes from 1 to capital N, of these delta ai. So, you know, usual situation with an integral here, right? What do? You add up finitely many areas, you take the limit as n goes to infinity, and you end up with an integral, right? So this becomes the integral from a to b of what you might call dA, right? But all that dA is just this in the limit. So what does it become? Well, it's the integral from a to b, 2 pi times f of x times ds. In this case, ds is with respect to x, right? And now there's a lot of different ways to write this, because this one could be written as our height y, right? That could just be written as y, and this could be ds with respect to x. So there's lots of different ways to write this, but this is the general idea, okay? This is y with respect to s. You could write this as y with respect to ds, right? So there's a couple different things. When you write this as y as a function of x, it doesn't really change much, but if you write this as y and then ds y, maybe that would be helpful, right? You just have a y here, and you can write your ds in terms of y. Remember, for you to be able to do that, you might have to chop up the curve a little bit to be able to represent the ds in terms of y, you know, most effectively. All right, well, all of this is just a basic setup so that we know what to do. What I really want to do here is do some examples. So our basic setup we'll call item number 1 of this lecture. Item number 2, we'll start doing examples. And so I want to compute, first of all, a couple of surface areas that we know the answer to so that we can compare. So let's start with the sphere. Sphere with radius rho, we'll say. And obviously rho will be greater than 0. So first of all, we know exactly what the equation of the sphere should be, but we want to set this problem up. We also probably know what the surface area of a sphere is. But we want to set this up so that this sphere is built the same way that we just set this up, right? So how are we going to do that? Well, we need to start with, we know that the equation of the sphere at the end of the day should be x squared plus y squared plus z squared equals rho squared, right? But we're going to do this as a surface of rotation, and we're going to do this by just plotting the portion of the curve in the first and second quadrant, right? And so actually what we're going to do is we're going to start with y equals the square root of rho squared minus x squared, okay, up here, and then we're going to rotate it about the x-axis. And so let's see how this works. Well, this is of course going to start here, right, at rho, and we're going to get a semicircle over to minus rho. This is our equation, y equals rho squared minus x squared. It's the top half of a circle. Now we're going to take that circle and rotate it out of the screen and then back through, and we end up with a sphere. Okay, so there's our sphere. So we want to compute the surface area of this sphere, right? How are we going to do it? Same way that we just talked about, right? So it's going to be at every point here, what are we going to do? So here's a point x. X is between minus rho and rho. We're going to think of a tiny strip around x. So a tiny strip around x that comes with a little surface area, or a little curve arc length element here, right? A little arc length. And then we're going to rotate that around. It doesn't hurt to draw this. I mean, my drawing is not great, right? But just getting a picture of what you're actually doing can be helpful. And then again, if we pull this out and kind of rearrange it so that it's easier for us to deal with, then we can break up the pieces, right? So this part right here, this is our ds. And the radius of this is just y, right? The radius is the height, which we can think of as either x or y. So the radius is it's y, or it could be written as rho squared minus x squared, right? So let's work this out then. Again, we need to find a formula for our ds, and then we'll plug it into our surface area equation, right? So we just found our area is going to be the integral from minus rho to rho in the x direction. By the way, I was a little loose with these, right? This should have been c and d up here. You guys probably told me that, right? Because this integral we changed to be with respect to y. We might have to do that down here. So let me fix it. All right. This one, in terms of the x direction, this is going to be 2 pi times the function rho squared minus x squared. ds is a function of x, or what's the other option? It's going to be the integral from 0 up to rho, right? That's a rho up there. So the other option is that it's the integral, still surface area, integral from 0 to rho of 2 pi y, with ds as a function of y. All right? So let's try to find ds, and then we'll maybe be able to choose which option we want to use here, right? So remember, ds has a couple different formulas. On one hand, ds is the square root of dx squared plus dy squared. All right. On the other hand, ds is equal to 1 plus, in this case we've got y as a function of x, right? So I'll write it as y prime squared and then times dx out here. All right. So let's see how this works. We need to, either way, we're going to have to compute y. We're going to have to find dy, right? Yeah, so another option is to just use this curve. So we have a couple choices here. I chose a very symmetric first example, right? So let's write this. Remember, we have our y equal to square root of rho squared minus x squared. That's perfectly fine. But where did this come from, right? This came from setting x squared plus y squared equal to rho squared, and just taking our y greater than or equal to 0, right? But of course, if we restrict our y to be from 0 to rho, then that's already taken care of, right? So let's look at this equation then. So if we take the y derivative of this whole thing, or the x derivative, it doesn't really matter. We just need the differentials, right? So either way we have to do, there's going to be something to do. Let's just take the derivative of the equation. So y prime is going to equal, so this is a chain rule, right? It's going to be negative 2x over 2 square roots of rho squared minus x squared. Then we need to square this. So I'm going to use, after all that conversation, I'm using this equation, right? So y prime squared is then going to be 4x, whoops, the 2's cancel, so let's cancel them right now. So these 2's will cancel, then we don't have to worry about them, right? So then it just becomes x squared over rho squared minus x squared. All right, and then we have to add 1 to this whole deal. So the next step is 1 plus y prime squared. This is all to find ds, right? And then we're going to go back up and plug back into this equation. So 1 plus this. Well, 1 we're going to represent as rho squared minus x squared over itself, right? You need a common denominator to add these up. Plus x squared over rho squared minus x squared. And of course, when this adds up, minus x squared plus x squared, those cancel. And we are left with then what? Just rho squared over square root, sorry, I'm jumping the gun here. It's just rho squared over this denominator, rho squared minus x squared. And then to get ds, we need to square root this whole thing, right? So ds is then equal to the square root of 1 plus y prime squared, then times dx, don't forget that, right? Well, when you square root this, rho is positive. This stuff, you can take the square root, right? And you end up with rho over square root rho squared minus x squared times dx. And at this point, now, so in my mind, I knew we wanted to get back to this y version, I think. But now, look what we have. We can rewrite this. This is y, right? And this shows up right here. And so this whole thing can be written as rho over y times dx. All right. Either way, we're still integrating with respect to x, right? So I'm going to leave it like this because then we can write this out a little bit easier. Now our total surface area is equal to the integral in the x direction from minus rho to rho. We set this up earlier, right? Integral from minus rho to rho of the height, right? The height of the function, which is y, times the arc length, which is ds, which we just computed, all times 2 pi, of course, right? So this then becomes 2 pi times y times rho over y, and then times dx. So this integral is with respect to x. Y is a function of x. All right, but look at in the integral, those y's cancel. And 2 pi and rho are constants. So this becomes 2 pi times the integral and rho, 2 pi times rho, integral from minus rho to rho of dx. Well, what's that become? That becomes 2 pi times rho times, this is just going to be rho plus rho. So times 2 rho, all right? And this all becomes, if you multiply this all together, it's 4 pi rho squared. That's exactly the right answer for the surface area of a sphere, right? Surface area of a sphere of radius rho is 4 pi rho squared. 4 pi times radius squared. And so we computed that using the surface area of a surface of revolution formula. So this is right. So that's good. All right, let's do another one. So this next item will be item number 3. Let's try to find the surface area of a cone. So again, something that we can compare to our intuition at least. Maybe you don't maybe you haven't memorized the formula for surface area of a sphere. It's one that probably when you see it looks familiar, right? Cone, same deal. So let's do a cone. Let's make this, when I say cone, I mean a right circular cone. Let's say exactly what we mean here. So a right circular cone with height h greater than 0 and base radius, let's call this r greater than 0. And so the situation looks like this. Usually you would draw your cone in this orientation. All right. So what's what here, right? With this one, this base radius, this is r, and the height here, this is h. Now there's a lot of ways. This cone can be moved around anywhere. And by the way, I just mean, when I say the surface area, I mean of the cone part and not the circle. All right, so not the base. So we should say that, right? So without the base. Okay, so we just want the surface of the cone part of the cone, not the base of the cone. So in other words, if you had like if you tip this upside down, this would look like a water cup that you get on a golf course, or a slushy or shaved ice or something when they have those cone kind of cups. I want to know the surface area of that. All right, so that's our job here. So there's lots of ways to set this up. I'm going to just, because it's already oriented this way, I'm just going to put our x and our y-axis here so that this points to the origin. And then I'm going to think about, if we were going to build this by rotating something, what would have to be rotated, right? Well, it would have to be this line segment that would get rotated, or it could be this line segment over here. But let's go with this line segment. And then how do you make the cone? Well, you rotate it out of the screen and around, right? So you rotate that around and it fills out the surface of the cone. So this green segment right here is exactly the thing that we want to focus on. So this is a line, right? This is a line that goes through a height. This point up here is at 0h, and this point down here is at r0. Right? So we've got 2 points, and we know exactly how this line is behaving. So the line goes through a height of h. So if we do like mx plus b, right, then the b is going to be plus h, and the height, or the slope of this is it goes over r and down h. So it's negative h over r times x plus h. All right, and you can check that. So that's the, and it's obviously negative slope, right? So This is the equation of the line. This is then what needs to be rotated around the axis, right? And we're rotating around the y-axis. As we build this thing out, our slices can go either way. All right, I wrote this as a function of x. If we're going to rotate it that way, right, in terms of x, then how are we going to interpret this? I'm trying to find another color. I'll use red. So we'll take our tiny values of x, right, and then the radius is actually the x value, right? The radius of the little strip that we make, the radius of the little strip, the little cylinder is going to be the x value, and the height is always the arc length, right? And so for this one, the surface area is equal to the integral from 0 to r, we're doing this in terms of x, 0 to r of 2 pi times x, times the radius, times ds. Again, ds is a function of x. Well, ds is going to come from this equation for y, right? So we need to compute that again, and I'm sure you've already noticed that takes up most of the work on this. There's setup, and then there's computing ds. So let's get right to it, right? So ds we're going to use as 1 plus y prime squared, square rooted, all times dx. All right, and so derivative, y prime, this is a linear function, it's just minus h over r. Y prime squared is just this squared then, right? H squared over r squared. And then our ds, we can just write it down, is the square root of 1 plus h squared over r squared times dx. This is a constant, right? This arc length is a constant. And that makes sense because our curve that we're rotating is a straight line. So the arc length is exactly a constant. Not only is it a constant, but we can kind of rearrange it, right? We can, just by adding these together and doing a trick like we did on the last one, we can write this as square root of r squared plus h squared all over r times dx. And you might remember from like a high school geometry course, this length right here, this L, or this, sorry, this number, I'm going to call it L. This number that I just highlighted, this is exactly the length, right, of the slant. It's the slant height. It's called the slant height of the cone, and I said L out loud and then I wrote H. That's L. So this is a constant known as L called the slant height. Again, I'm sure you did this in a high school geometry course. That's the slant height of the cone. And so our ds is just equal to slant height divided by radius times dx. All right, and so this integral is going to be pretty straightforward. We've got, remember, that L over R, that's a constant, right? We've got our 2 pi, that's a constant. So we need to integrate up x dx. This x is left over, though, right? So when we take everything out, we end up with 2 pi L over R, integral from 0 to R, x dx. All right, let's see what happens. Well, we get 2 pi L over R. Antiderivative here is 1/2 x squared. X goes from 0 to R. The 2's cancel. All right, and look what's left. We have, this is going to be r squared, right? But r squared over r is going to cancel. I'll write out all the steps. This is pi L over R times r squared minus 0. That's just r squared, r over r, so we get pi times L times r. All right, that's the surface area of just the surface of the cone without the circular bottom. All right, and that's exactly what it should be. Again, you need to remember what L is, right? So where L is equal, if you want your answer in terms of R and H, then you have to put back in. So I only wrote the L because we might remember that as being the slant height. But if, like, for example, in your homework, you might have to put it in terms of R and H. What would it be? It's going to be pi times the square root. I'm going to move this so that pi times R times the square root of R squared plus H squared, which is just L, right? So this is the same. It's just a different way to write it down. Okay, so a couple examples that we already knew the answer to, and we got the same answer by using this method. So, you know, if nothing else, that's justification. Now we at least halfway believe that the method works. It's not a proof, right? But the method does work, so it makes perfect sense. So here's the next example. This is number 4. This one's called Gabriel's horn. This is one of my favorites, so this is very exciting. So this one, here's the setup. I'm going to build this horn, this so-called horn. So here's what we're going to do. I'm going to take the curve, y equals 1 over x. That's a hyperbola, but I'm going to take it for x greater than or equal to 1. So that's a portion of a hyperbola that goes off to infinity. So I'm going to draw this way. So here's our x-axis, here's our y-axis, and the portion of the curve that we care about, should be a height of 1 and an x value of 1. It doesn't matter if the scales are off. There's that, right? And then this is going to slowly shrink down this way, right? It's going to get smaller and smaller. The equation is 1 over x, right? And so Gabriel's horn is the shape that you get by rotating this curve around the x-axis. So what's it going to look like? Well, I want to do that in a slightly different color. So it comes down here, and then it pinches up here. It should be completely symmetric, right? And it's not, because I drew it. But the idea is that all these little circles are shrinking. The question becomes, are they shrinking? How are they shrinking, right? But this surface, just the surface of this thing, is a surface called Gabriel's horn. All right, I want to know two things. So 2 questions. Question 1, let's start by computing the volume of this thing. So let's try to remember how to compute the volume from Calculus 1. So I'm just going to write this as volume, question mark. And then question 2, surface area. So this is our new question. All right, volume and surface area. All right, well, let's take a look here. The volume we can start with. So how do you do the volume? Well, the volume can be done many ways, but one way is to just do this by slicing method. So where I drew these discs, slice these, take them out, and instead of treating these just like circles that we're adding up, or like little cylinders to add up the surface area, we actually find the area of these slices, right, and add up the area of the slices. So if this is a slice in the x direction, then the height of this thing, or the radius, is 1 over x, right? And so then the area of this slice, radius of x, is pi times 1 over x, quantity squared. And then we just add these up in the x direction, right? You just add up the areas of these slices, and that'll give you the volume. So for the volume we use the slicing method. It's going to be the integral from 1 to infinity. So we're going to have to treat this like an improper integral, right? Volume from 1 to infinity of this area function times dx, right? We add these all up. The area function we wrote down is pi over x squared. So this is integral from 1 to infinity of pi over x squared dx. And now we have to, the pi can come out because that's a constant, and then very carefully deal with the improper integral. So the pi comes out. Remember how we deal with improper integrals. We swap out the upper bound with a t. We have the finite integral, right? We compute the finite integral for any t, and then we take the limit as that t goes to infinity. All right, this t has to be bigger than 1, of course. So the idea is to move this slice outward, right? And then capture all of the volume that you've enclosed as you do that. So what do we do? Well, now we have to integrate, right? So this is our pi. Limit t approaches infinity. Antiderivative here is negative 1 over x, as x goes from 1 to t. And this then becomes pi times the limit as t approaches infinity of this. When you rearrange it, becomes 1 minus 1 over t. All right, as t approaches infinity, 1 is constant. 1 over t approaches 0, right? And so this approaches pi. And so the volume of this horn is pi units cubed, right? Pi units cubed. That's the volume of this horn. So it's got a finite volume. In other words, if you were to try to fill this, if this was measured in, gallons or something, then if the volume was measured in gallons, if you were to fill up this horn with paint, you would have to pour in pi gallons of paint to fill this thing up, right? But you could fill this up. You'd have to turn it on its side and pour in the paint, and you would fill up the horn with pi gallons of paint, even though it pinches off to infinity, right? Well, now let's check the surface area. So the surface area we have to do a little bit differently, right? I'll draw in this picture, and then we'll write the formula. So for the surface area, it's very similar, right? Except remember the formula is different. So now we have to look at the cylinder. And the cylinder has these properties, right? Well, what's it got? It's got the height of the cylinder, which is this part right here. That's the arc length, ds. And the radius of the cylinder, this part is now the y value, actually, right? That's the y value. or 1 over x. All right? So let's compute this and see what happens. Or let's at least write it down, right, and see what happens. So, and of course we know that the formula for the surface area is pi times, in this case, y times d. It's 2 pi y ds, right? It's the circumference of the circle times the height. Yep, 2 pi y ds. So here's our formula for the surface area. The area is equal to, again, integral from 1 to infinity. That part's got to be the same, right? We're going to write our ds in terms of x, at least to start, and we can change it if we need to. But this is going to be 2 pi y. ds is a function of x. And then, as always, we need to compute this ds, right? So this is for the function 1 over x. So let's see what happens. So our ds is, again, 1 plus y prime squared times dx. Y prime, so y is 1 over x. This means y prime is negative 1 over x squared, which means that y prime squared is 1 over x to the 4th. Okay? And then when we add this all up, so then so the square root of 1 plus y prime squared, when we add this all up, what are we going to get? We are going to get something like this. So if you add this up, it becomes x to the 4th plus 1 over x to the 4th. And then this is like x to the 4th plus 1 over x squared. All right. And maybe I didn't even want to do that, but what we're going to do now is plug this back into the integral, right? And we can even leave the y as 1 over x. We know the formula for y. So our area here is going to be the integral from 1 to infinity of 2 pi times 1 over x times, I'm going to write this way, square root of x to the 4th plus 1 over x to the 4th times dx. All right, and this is an improper integral, and the question is, does this thing converge, right? Number one question. And then obviously, if it does converge, it would be nice to know what does it converge to. But look at this. So we want to actually take a look at this term. This term right here, the way I've written it, maybe it would have been even better to leave it slightly differently, but this is, I'll rewrite it the way we built it, right? It was like this, 1 over 1 plus x to the 4th. X to the 4th is getting very, very large, right? But no matter what, this number is still always going to be a little bit bigger than 1, right? And by the way, it's going to be, obviously it's bigger than 1, so it's positive, right? It's a positive number that's bigger, slightly bigger than 1. So what that means then is that our integrand, so this means that our integrand, 1 over x, the 2 pi can come out, right? 2 pi is a constant we can deal with later. But this 1 over x times ds, which again I'll rewrite, 1 over x to the 4th, this is always bigger than 1 over x. It's just slightly bigger, slightly larger than 1 over x, right? And what do we know? Well, we know that the integral from 1 to infinity of 1 over x dx, this is the cutoff, right, for the p-test. This integral, in terms of the p-test, you might say it fails the p-test, because this is like 1 over x to the p, where p is equal to 1, and this integral diverges, right? It's divergent. And you could say, well, how is it divergent? Well, it equals infinity, right? In some sense, the surface, so the area under the curve 1 over x approaches infinity. It never approaches a finite number, right? It keeps getting larger as you go further and further out the curve. And by the comparison test now, so we talked briefly about the comparison test in the last lecture, but by the comparison test, so the comparison test, our integral is bigger than that, right? So our integral is bigger than a divergent integral. What does that tell you? Well, it must also be divergent, right? So this area from 1 to infinity, 2 pi x square root 1 plus 1 over x to the 4th dx, this must diverge. And so the way that you can interpret this is what? Well, that means that the surface area of this Gabriel's horn is somehow infinite, right? It's infinite. And so thus Gabriel's horn has finite volume. We computed this, right? Finite volume. We found that it was pi units cubed. So we could fill up the whole horn with paint if we poured the paint in it, right? But it has infinite surface area. Well, what does that mean? That means that if we tried to paint the outside of this, we would never be able to finish, right? Infinite surface area. Okay, so that's a really interesting example. Gabriel's horn, it's a surface with, it encloses a finite volume in 3 dimensions, but its 2-dimensional surface area on the surface of it is infinite. All right, very interesting. All right, I've got one more example. This one I'm just going to start setting up and leave for you guys to finish, and that should be a hint. In other words, this is a really good candidate for a test question on the next exam. So make sure you finish this one. This one is called the torus, so surface area of a torus. So surface area of a torus. So I'm going to do 2 things. I'm going to tell you what a torus is, and then I'm going to help start setting up the integral, at least make a couple of choices, and then I'm going to leave the rest for you guys to do. All right, so here's how you build a torus. You start, there are lots of ways to do this actually. I'm going to start this way though. And then we'll all be on the same page. So here's our y, here's our x. Let's start with a circle of radius little r. We're going to need 2 radii here. So let's start with a circle of radius little r centered at the origin. Okay? So in other words, the equation of this circle is x squared plus y squared equals little r squared. And then let's say there's another radius, so another r, big R, which is bigger than little r. And I want to rotate this circle around the axis x equals r. Okay? So this is how we build a torus. It looks something like a donut. And we're done. So maybe we're losing the picture here. But the idea is we've taken this circle, rotated it around, and I want to know what's the surface area of this thing. So can we compute the surface area of this shape? So this is a torus. So it's obtained by taking the equation of the circle of radius little r centered at the origin and rotating it about the axis x equals big R. All right, and then the rule here is that little r has to be less than big R. And that should make sense because we want to make sure that there's a hole in the middle of our donut, right? So again, if we were to kind of just sketch this thing, it looks something more like this. We take the red circle from here and we rotate it around this way. So its center can be thought of as being rotated around this way. All right, so in this picture, what do we have? We have the radius of this circle is little r, and the radius of this circle that starts here and goes to here, right? That radius is big R. Yep, and so that's a torus. All right, we want to find the surface area. Well, how are we going to do this? We need to chop this up somehow. It's rotated around this x-axis. So to get our cylinders, we're going to have to go this way. And then we notice that we have a lot of symmetry here, right? So we either have to do this in 2 parts or we have to cut this thing up in a way that we can make sense of by just kind of doubling, right? So here, that's the way I want to do it. So let's say that we think just of the top half of this original circle. The bottom half is symmetric and it's rotated symmetrically around this thing, right? So we're going to compute half of the surface area by looking at this circle. All right, and then what are we going to do? Well, as this gets rotated around, we really just want to look at a small portion here, right? So for some x value, we look at a tiny dsx up here, and this gets rotated around to create our cylinder right up here. So there's the cylinder that we're going to pull out. We're going to add this up as we go, as x goes from, so x is going to vary. X is going to vary from minus r to r, and then we're going to add these up and we're going to get half of the surface area, right? So half of the surface area is going to equal the integral from minus r to r of what? The height of this thing is, the radius of this thing. We need to go by the radius of this circle, right? So the radius of this thing, so we have 2 pi times the radius of this thing. I'll do it in orange. The radius is this, right? The radius is r minus x, big R minus x, Okay, and then the arc length here has to be computed. I'm going to let you guys compute the arc length from here. So we've done this one before actually, but arc length from here. So that little arc length element comes from that, right? So ds of x. All right, so 2 pi times the radius times the height, and that's what you're going to get. So this is the setup. This is the function that you're going to use. So use this for your ds as a function of x. And then very, very carefully integrate this, and don't forget this 1/2. All right, don't forget this 1/2. So feel free to ask questions about this if you get stuck, but this is the idea. So yeah, this is for the interested student, who is, I hope, everyone in this class, but finish this. So compute this integral. Make sure you can compute the arc length element properly. Carefully compute the integral. And then don't forget about this half. And the half comes, by the way, because we have cut the donut in half this way, right? We've cut the donut in half. So you're really just, when you're done, you're going to have computed the surface area of half a donut, half a bagel, you might say, right? Okay, so I'm going to leave this here, give you guys some time to work on this, and let us know if you have any questions moving forward.